All right. Um, Quiz is already up. You can go ahead and start working on that. True. That's true. True.
You can sneeze.
Thanks. Who'd like to start us off with a prayer? Do you want to?
Sure.
Here, I need to talk into here.
Does this work?
It should.
Wow. Okay. Our dear Heavenly Father, we're grateful for this day. We're grateful for the opportunity we have to be learning more about calculus today. Please help us be able to understand the topics and be able to understand and learn. And I say this in the name of Jesus Christ. Amen.
Thank you so much. All right. I'm wearing my Polynesian garb today because obviously I'm a Polynesian. Now, I served my mission in New Zealand. I served in some Samoan wards there, learned a lot of Samoan. But today there's a conference for Polynesian students today. It's called the Kahanui Summit. A group of professors here, not me, I wasn't part of it starting this off. They wanted to do something for the Polynesians and help more Polynesians go to college and more Polynesians that are in college go to grad school. So they have a different emphasis over the years. And today it's a focus on getting Polynesian students that are already here at BYU looking at going to grad school. Polynesians as a whole, even though they might do as well as other people in high school, they have a lower rate of attending college. So they don't believe, in general, they don't believe themselves to be college material. So do what you can to change that stigma, okay? One of the big things, actually, that BYU Pathways does is they convince people that they are college material when they start the program. That's a big thing that they do, is that they belong in college and they can succeed in college. The other big thing that they do is they move value up in the college degree. So your first year, you end up with a certificate that you can go out and get a job with, instead of waiting at the end of the 4 years till you finally have something you can go and get a better job with. Pathways does it in a different way. So you can, by the end of the year, you have something that can improve your position. All right. Take another minute or so here. Okay. I'm going to go to a different screen. If you still want to see this, just take a picture of it or something. So we'll come back to it before the end, but I'm going to start talking about average value of a function in general. It'll still give you time to work on this. So Okay, can you guys see the video? Okay, here we've got a diver. He's on a 1 meter springboard. Where I have it now, I think he's just about ready to bounce down and then take off. So I'm going to say that he goes about 2 meters high. So 2 meters, 2 meters is about 6 feet 6. Most divers are shorter than 6 feet 6. So maybe, oh, that's not working. But anyway, so somewhere between his head and the top of his hands, right? It's going to be about 2 meters. So we'll look at like the bottom of his body when he's up spinning around. We'll see where that goes. So, oh, that didn't work very well. Here, it might show it again. Maybe. No, it's my slow computer. So
62.35. Joseph Safelli.
Okay.
Purdue University, 205C.
New guy's coming up. Okay, this is the guy I was trying to get on. So probably about the top of the, oh, come on. About the top of the rail. So, yeah. Nice. It's already going frame by frame for me. So. Oh, I tried to pause it, but it was too late. But he did get up there about the top of the rail on the edge. Okay, so my question is, as this guy leaves the board at 1 meter high, goes up and he spins, we'll say at 2 meters above that, so 3 meters high, and then he lands at 0 meters high, at the level of the water. So it goes from 1 up to 3, down to 0. What is his average height during that trip? What is the average height during the dive? Now, just take a guess. So think about the situation, think about what you know. What would you say? What's your estimate? And then tell your neighbor. All right. Tell me what some of your estimates are. What? 1.5. Okay, 4/3. Okay. What was it? 44 pi thirds? 44, wait, divided by pi thirds, or 44 times pi in meters or inches? Okay, what else? Anyone? 1.3. Okay. Anyone else? All right. So I know where 4/3 came from. Who said 4/3? How did you get 4/3?
Well, since they didn't give us a quantity of time, I just added 1, 3, and 0 together and divided by 3.
Okay. So those were 3 values that you knew on the trip: a beginning, a middle, and an end. So you can average those. You can do that with the nice algorithm that we teach you guys in 5th grade or whatever it is. You get 4/3. Okay? So finding average values when you've got a list of numbers is something you guys have known for a long time. You add up all the values and you divide by the number of values that you have. Right? So you sum the values and divide by the number of values. Okay. How many heights was our diver at during the dive? He was at infinitely many heights. Right? Any moment of time he was at a height. So this strategy here no longer works for us because the number of heights he's at is infinite And if we added up all of those heights, what would we get? Infinite. And so we're kind of toast trying to do this strategy. So we have to think about this in a different way. So how can we think about averaging values in a different way? Okay, here's a 4, a 3, and a 2 in block towers. Okay. There's a different way to think about averages, and that is at least the arithmetic mean. Instead of thinking of that algorithm of adding them all up and dividing by the number, really what you're doing by doing that is, if you imagine each of those numbers as a tower, you start taking from the high ones and putting it on the low ones until every tower has the same height. And then the height of all those towers, when they all have the same height, is the average value. Okay? And the reason that algorithm works of adding up all the values and dividing is when you add up the values, really what you've done is you have found the area of a weird shape. You found the area of that shape, and you have divided by the length of the base, which in this case is 3, and what you got out was an average height. So that's your average value. Okay? So if we think about it this way, then we have a strategy that we can use in odd-shaped things where we can't just add up the number of blocks. So, for example, if I want to find the average value of this function from here to here, then I can calculate the area, or at least the net area, with an integral. All of this area is positive. This area would be considered negative, and I would get maybe some value about right there, right? And so this rectangle right there would represent the same area, the same net area as the function, and this height would be the average value. So to calculate the area of that, we can use the integral and divide by the length of the base. So that's how we're thinking about average values of a function. So let's go back to this problem. So we have our function here. Oops. I didn't put my dx at the end. I tried to put it down there as a bound. X equals 1, x equals 3. And I need to divide by the length of the base, which is what? 2, which I get from 3 minus 1. And then I can do this calculation. So antiderivative x cubed, x to the 4th over 4. Antiderivative of 1 is x, going from 1 to 3. And if I plug in 3, I get 1/2. 3 to the 4th over 4 plus 3 minus 1/2. 1/4 plus 1. And I'm going to pull out the 1/2 to begin with. And here I get 81/4 plus 3. And here I'm going to have minus 1/4 and minus 1 after I distribute those out. So I end up with 80/4 plus 2. Why am I doing this? Well, I need to stop. Stop. Oh, dang. I'm just telling you guys the answer. Okay. All right. I almost told you guys the answer. Most of you had it anyways. So what I get 20 plus 2, which is 22 divided by 2, so I get 11. So 11 is the average value. Okay, any questions so far? Okay. All right. So we're actually going to calculate the average value of that diver's height. So I have already done. You know I wasn't an English major. I have done some of the work for you. Okay, so there is the equation that gives his height for any time t. Okay, the 1 at the end, that makes sense because at time equals 0, you get 1 meters. Okay. So here's 1, 2, 3. Graph looks something like this. Okay, where this is time. Okay, your job is to figure out what the average height is. Okay, you can work with a neighbor. Go ahead. You're welcome to use something to solve for the, when you set that equals to 0 to solve your gun, you don't have to do that by hand. Type it in your calculator or pull from Alphas. Type it into this to the point where it's Oops. Okay, so if you're following my work up here, I'm using 10/7. It turns out that that's the exact value. It's 10/7 instead of a decimal approximation. Turn on my mic here. And it turns out nice because I'm evaluating at 10/7, but I am multiplying by 7/10. So as I multiply that in here, really what I'm doing, every 10/7 that I have multiplied in each of those terms times the 7/10 becomes a 1. So I basically lower the factor, lower the degree of each of those by 1. So, and it's nice that I have 4.9 here and I have 7 squared in the denominator. So that just becomes a 0.1 over 3 times the 100 plus 7 into 63 will be 9. So I end up with 0.9. 0.9 times the 2 into 10 will be 5 plus the 1. So here I end up with 10/3 plus 0.45, or sorry, 4.5 plus 1. 10/3 is what, 3.3-ish? And that's a negative point there. So if we approximate that first one to 3.3, you end up with 4.5 minus 3.3, which is 1.2, plus 1, we're at about 2.2. 2.2 meters high on average. That's higher than any of the estimates that we got. Why is it so high? Someone want to take a stab and explain why is his average height so high? Really loud. That's right. So that's one nice way to think about it. This guy doesn't spend much time below the board. Okay, he's going really fast by the time he gets to the board level of the board, and so that doesn't get much weight there. But he's slowing down up here, and then accelerating down towards the water. He spends most of the time up here, so higher than you would expect. But yeah, on average, 2.2 meters. He gets up to 3 meters above. But on average, he's 2.2 above. All right, that's not a very important, life or death situation. But I am going to explain a situation, just in general, where this is important, and it has to do with car crashes. So when you've got a car going fast, there's a lot of momentum, and when it runs into something, all of that momentum gets transferred somewhere. And the rate at which it gets transferred is called impulse, if I have my physics correct. I had a friend in high school. He had like a 1972 Buick car. It was really long and big. It was built like a tank, drove like a boat, and he actually did get in a wreck with it. But it wasn't a serious wreck. He got in a wreck. It hardly touched the thing. I mean, it was solid. They don't make cars solid anymore. And I always thought when I was in high school, I was like, I want a solid car, so if I get in a wreck, my car won't get hurt, right? I don't want to pay for getting it fixed. That's not very smart of me. Why not? Well, if I was in my friend's car and ran into a tree, then the amount of time that goes from the time I first hit the tree to the time that my head hits the steering wheel is not very long. And that impulse ends up looking like this, where this level is probably where my brain gets crushed. Okay? So the reason they don't make cars like that anymore is what they're trying to do is, instead of having something like that, they're trying to spread out the amount of time that it takes for all of that momentum to get out of the car. So they put crumple zones in the cars now. So the same area that we're talking about there gets spread out over a longer time. And also the airbags and your seat belts, they help it also to spread out and reduce the maximum value, the maximum impulse, and try to get it as close as possible to the average impulse. So maybe they could even get it even better with those things. Oops, that wasn't very good. But anyway, physicists work on this, trying to figure out how do you minimize the maximum impulse in a collision. Okay. Let's do another non-life or death situation. I don't want to scare you guys. Okay. It's not life or death, but actually this is an unsolved problem in mathematics. It's not a super important problem, but it is unsolved. I'm going to explain the problem in terms of a context. So, suppose you have a wildlife park that is 2 miles across. So from here to here, it's 2 miles. Okay? You want the rangers to be able to drive around a lot of those places in there, but you don't want to put a lot of road in the wildlife park. It's a wildlife park. You want to keep some of it wild. So you have 2 miles of road that you're going to put somewhere in this park. Okay? It's going to all be connected. Doesn't have to be connected to the boundary. Okay? But how would you want to build that road? What would be a good idea on how to build that road to help your wildlife park the best? Oh, someone said, oh, you're saying a circle. So it would be nice to be able to get to areas of the park on average as quick as possible. And especially in this case, we're worried about the boundary because that's where most problems happen on the wildlife park. So the question is, how are you going to build the road in here so that on average it's closest to the boundary? And one option, oops, my eraser's not working. One option is you could take 2 miles and go like this. You could also take 2 miles and go straight across. And I bet you guys can come up with some other ideas. So at your seats with your neighbors, see if you can come up with something better than these. Otherwise, you can just chop it up into lots of little pieces and run around the outside. Yeah. Got to be connected. It does. Connected and continuous. Oh, yeah, you can have a fork. Yeah. You can do something like this. So, yeah, that's good. All right. What options? Anyone have a good option? You're going to write your name. Write your name with the road. So, yep. Okay, so something like this. Right? Okay. We can't go all the way through the middle because we've only got 2 miles of road. And if 2 miles gets us from one edge to the other edge, that's what we got. Okay? Any other ideas? Oh, okay. So someone in my last class talked about a peace sign. So you could do something like this. Is that kind of what you're thinking? Or something like that? Okay. Yeah. A triangle. So you can try a triangle. You might try even getting rid of this line of the triangle and having just 2 lines like this, and you'd be able to move closer to the boundary maybe. You're losing access to these points, but you're getting closer to almost everything else. Okay. Here's another one. This one, this idea here, that if you have 3 points, the shortest amount of road you could connect those, or fencing, or string, or whatever, it looks kind of like a peace sign where these angles are 120 degrees. Okay. And so one option you might think of, instead of 3 points, you might stick 4 points in there. And the shortest amount of fencing, or the shortest amount of road, shortest amount of perimeter to connect these is that. And all of these angles are 120 degrees. That's called a Steiner H. Okay? This is a nice thing to know when you're playing Ticket to Ride and you've got destinations at kind of like the 4 corners. You want your roads, to minimize the number of trains you do, to be something like that Steiner H. Okay? So I use that all the time in Ticket to Ride. Okay. So we're actually going to just compare these first two. I've actually had the computer do a whole bunch of these, but it's been a while. I can't remember which one is the best. What we think is the best, I've had a colleague work on this, a mathematician. He thinks it looks kind of like this, where this curve is a hypocycloid. And near the end of the semester, we're going to talk about cycloids. Remind me then, and I'll tell you what a hypocycloid is. Okay? Or you can think about it as taking this circle here and breaking it and trying to let it open up and somehow moving it towards the boundary in an optimal way. All right. Well, we don't need calculus to figure out what this average value is for this one. The radius, the distance from the center out to the outer one, is 1. And if I have 2 miles in a circumference, then if I divide by 2 pi, that will give me my radius, and the difference of those will be that distance, and that's going to be my average distance anyway. If you give me a something happening on the boundary, then I'm going to go to the closest point on the road and go there. We're kind of we're going to assume you can go really fast on the road and it's really slow on going through the jungle. All right. So this is about 6.68 miles on average. Okay. All right. Well, what about this other one? Straight across. You guys think this is better or worse? Worse? I hear quite a few worses. Worse I don't know. Okay. So if something happens here, how far is it? what's the closest place to my road? Straight down. So if you're the Rangers, you're not going from the edge to the road. You're going to drive to this point on the road and head out. Okay? So things are happening here, and we're going to all of those. The way we have to model this, we have to think about all of our points are the ones on the outside. They're not the points that we care about along here, along the diameter. So I'm actually going to model this with all the points on the outside as an angle, or radians. Radians, remember, is the distance that how many radii you need to go around. So I'm going to measure it in terms of theta. And sine of theta, if you give me a theta, the distance straight down is sine of theta. We don't even have to multiply it by anything to get the units right because our radius is a mile. So sine of theta, if I'm there, sine of theta, if I'm there, sine of theta. And for our problem, if to find the average value, I only have to worry about 1/2. I don't have to worry about the lower half because the average of 1/2, it's symmetric, is going to be the same as the other half, which is going to be the same as the whole thing. So how am I going to use this? To try to write down right now, what expression would you write down to find the average value of, the average distance to the boundary of that road? I see a lot of people wondering, what am I going to do here? How about this? Let's start with the bounds. What are all of the bounds? What are all of the theta values, the points that I'm measuring the distance to? 0 to pi. I could do 0 to 2 pi if I wanted to and go all the way around, but I'm just going to focus on half. Okay. It keeps me from having to worry about when sine is negative, because here I don't want to worry. I don't want negative values. It's going to cost me gas and time whether I'm going in a positive direction or a negative direction, right? So my function is sine of theta, d theta, and what's the length? 1 over pi, or really pi minus 0, so that's where you get the 1 over pi. Because really what we're doing is we're taking this piece. Here, let me get another color. We're taking this distance here, and then we are stretching it out along the x-axis, and we're letting all of these lengths stick up perpendicular to get this, which is the sine function. So we're finding the average value of this function here from 0 to pi. Okay, well, this is something we can actually do. Antiderivative of sine, negative cosine. We're going from 0 to pi, and a negative cosine of pi minus a negative cosine of 0. What's cosine of pi? A negative 1, so minus a negative 1 gets us a 1. Cosine of 0 is 1. So I get another plus 1. Back to our favorite 1 plus 1 problem. And I have to divide by pi, so 2 over pi. Someone punch that out on their calculator, and what do we get? 0.64. So it is better than the circle in the middle. On average, it is closer. You get some that are really close. You get some that are further away, but on average it is better. So, and in terms of miles, it's about 180 feet. I guess it's not in terms of miles, but you can, in terms of feet, it's about 180 feet. So, all right. Let's go back to this problem. Okay, in your reading, you would have bumped into something called the the mean value theorem for integrals. The mean value theorem for integrals is similar and closely connected to the mean value theorem for derivatives, but the mean value theorem for integrals is stronger. It's stronger because this says something for continuous functions. The mean value theorem for derivatives, you have to have a differentiable function. So, because there's more continuous functions than differentiable functions, we consider it stronger. And what does that mean? Well, we got the value of 2.2 as the average value, right? We're going to say that that's right here. So, if the function is continuous, the mean value theorem for integrals says if the function is continuous, then there is some value. They call it C. There's some C that exists, can have more than one, where the function value actually equals the average value. If we think about it, hopefully that makes a lot of sense. Because if you imagine, think of an ice block here, melting, and all the water goes to this level, then the ice block, some of the ice block had to be above that, and some of the ice block had to be below that. Unless your ice block was already like this, then it was all at that level. So any C exists. So, or any value here would be your C. Here we'd have a C here that would satisfy the mean value theorem for integrals. We've got one there. So sometimes the book will ask you to actually find the C that satisfies the mean value theorem. With this problem, with our diver problem, how would we go about finding that C? At what time is the diver at his average height? Because the mean value theorem says if his height is continuous, and I didn't see him teleport. Did you guys see him teleport? Well, actually, kind of. It did flicker a little bit. If you could teleport in diving, you would never make a splash. I mean, right? You could do your tricks and then teleport underneath the water. That would be really slick. But, all right. So how would you actually go about finding the time when the diver's height is equal to the average height? So tell your neighbor. So. All right, someone give me an idea. You set your average. What do you say your average? The average value, 2.2 equal to. Oops. All right, so this tells me the height at any time. This is the height I want to know, the time he's at. And so then you can go ahead and solve from there. You should end up with two values. So either of those. I don't know what those values are. So you could, what do you get him? What do you get? And 1.05 seconds. All right, so he's spending 3/4 of a second above the average value there. right? That's pretty good. Because he's only in the air from 0 to 1.4-ish, right? So he's spending about half the time, more than half the time, over the average value. The value that he would spend half the time above and half the time below, we wouldn't call that the mean value. What would we call that? The median value. So, okay. All right. Any questions about average value functions or the mean value theorem for integrals? All right. Well, I'm done. Have a great day.